At Sensient, we produce open path gas detection sensors. Every gas absorbs light, and really what we're doing with enhanced laser diode spectroscopy is we are using laser light at a very specific wavelength to get a particular reaction from that gas, which then enables us to identify the gas.
Toxic gas detection needs to be done at very low levels, parts per million, much lower than can be done with NDIR technology, which has forced people to use very poor technologies like electrochemical cells and semiconductor films, both of which are non-specific, react to all sorts of things and are prone to failing without any warning. We thought that was completely unacceptable and that operators needed to be protected by something far more reliable.
The main challenges for toxic gas detection is the small concentrations we're trying to detect being target gas specific, so we don't have unwanted shutdowns due to other interference gases or environmental effects. To have a fast speed of response and a reliable response in adverse weather conditions. In addition to that, routine testing or maintenance is a significant burden on any operation. Sensient ELDS technology addresses all of those issues.
ELDS stands for Enhanced Laser Diode Spectroscopy, which is the technology that has been developed by Sensient.
All gas molecules interact with light. At certain wavelengths, gas molecules absorb energy. This generates an absorption spectrum. Each peak represents an absorption line. Sensient uses advanced lasers that are precisely tuned to a specific individual absorption line. Taking ammonia as an example, a single absorption line is selected and a laser is scanned across this absorption line. This generates a signal as the laser beam passes through the gas. The signal, called a harmonic fingerprint, is unique to ammonia. Our detectors use a transmitter that directs the laser beam towards a receiver. The receiver is programmed to recognize the specific harmonic fingerprint of ammonia, avoiding false alarms. If interference gases or adverse environmental conditions exist, the harmonic fingerprint observed by the receiver will not match. During an ammonia gas release, an ammonia-specific harmonic fingerprint is observed. This will match the one programmed in the receiver and confirms the presence of ammonia. The receiver then calculates the gas concentration in the beam. This is done by measuring the amplitude of the harmonic fingerprint. As gas concentration increases, so does the amplitude of the harmonic fingerprint.
Dual laser technology is unique to Sensient. There are certain gases that are very difficult to detect. For example, hydrogen sulfide or H2S, because it produces a very weak signal. The way we overcome this is by using two lasers, and it is only when both lasers produce a harmonic fingerprint match that an alarm is triggered.
In toxic gas detection, by having two lasers, comparing the results, you completely eliminate the false alarms that you get from having a single laser.
So the three key things to take away about Sensient's toxic gas detection is fail-safe operation, no false alarms, and there are no consumable sensing elements. For the first time in many years, we've got some new sensing technology which offers some real benefits to end users and operators of this sort of equipment.